So here we are at the Hartz Range, or the Hartz Mountain National Park. We are, I think, on the 3rd of November today, which is, a month before summer starts. And as you can see, it's a fair bit of snow at the moment. We're about 800 metres above sea level. Whilst not entirely common, this is the kind of weather you can expect in Tasmania, and it's a very maritime place, very steep, vertiginous mountains. So you've got a lot of moisture in the atmosphere. All you need is a bit of a Antarctic, bit of winds down from the Antarctic, and cool things down enough to get a bit of a snowfall. So here's late spring in the southern ranges of Tasmania. So we're right down the southern tip of Tasmania at the moment. You'll notice around me there's a bit of a snow, powdered with snow. But there's a different type of vegetation than you might expect, or what we just encountered at Darwin Crater, where I've just come from, over on the west coast. So if we just walk over here, you can see that this here is Eucalyptus coccifera. Now, the eucalypts are a bit of a game changer in Tasmanian ecology. They're a plant that is termed sclerophilous. They're adapted to nutrient deficiencies, and that's given a kind of a very hardened structure in its leaves. They're full of volatile oils, and they're extremely flammable. Actually, they are very, very, very flammable. They migrated through time from mainland Australia, sort of facilitated by the slow drift of Australia into the subtropical latitudes, or the sort of more extratropical and Antarctic latitudes, where it was much wetter and cooler. As Australia's drifted north into the subtropical latitudes, it's got drier as we rifted from Antarctica and the rest of the Gondwana continents. It's got drier, so this aridity combined with the really poor soils that you get in Australia have facilitated the radiation of the sclerophyll flora, and the eucalypts chief among them. So the other thing that's really facilitated the spread of the eucs is fire. So this combination of aridity and fire, and a positive feedback between how flammable these eucalypts are and a drying climate which really favours burning, has really allowed eucalypts to radiate all over Australia. And there's over 700 different species of eucalypts. They're found from the highest peaks in here in Tasmania as a dwarf Krumholtz little plant. The tallest flowering plant in the world is a Eucalyptus regnans, mountain ash, which is also found in Tasmania. They're found in some of the driest areas of Australia, in the deserts. Found on rivers. They're found in just about every niche you can imagine. The one thing that unifies the majority of them, there are some species that can reproduce in the absence of fire, is that their reproduction is either dependent upon or really enhanced by disturbance by fire. And that can be through the release of seeds triggered by heat, or it can be via clearing of the ground for competition and the fast regrowth, or a combination of these sorts of things. Other adaptations are rootstocks underground, lignotubers, that you can basically burn the whole top of the tree and you'll get quick resprouting out of the rootstock that's insulated from the fire from the soil. A whole lot of different adaptations that either are very explicitly fire adaptations, or adaptations to other things like water deficiencies or water shortages is one of these reasons that you get a big bulbous rootstock in many plants. And that is a co-adaptation to fire. It also conveys advantage to plants and for disturbances such as fire and maybe browsing and some other things. So why were they a game changer? Well, what's happened is, as I said, as Tasmania and Australia have drifted north, eucalypts have spread. And what's happening now, and what's happened through the Holocene, and particularly on this mountain range, we've done a lot of research here, and we've actually mapped this process is that as climates kind of become more variable in the late Holocene, after about 6,000 years ago, the El Nino Southern Oscillation really ramped up in the tropical Pacific, and that gives this periodic drying out of eastern Australia and eastern Tasmania, and stretching further west. Periodic drying during El Nino events, during the warm phase of the ENSO, El Nino Southern Oscillation. Then you'll get anomalously wet conditions in La Nina. And this sort of phasing, this variability, has been ramping up. You know, you'll get centennial, hundreds of years of lots of El Nino events, and then periods where the system seems rather quiescent, it's sort of rather silent, and you get a bit of stability, then it's ramped up again. And these phases correspond discretely with increased fire in areas like this, in these southern ranges. So if you go back before the ENSO system sort of ramped up, all of this was covered in rainforest, and rainforest dominated by fire-sensitive conifers, long-lived cupressaceae conifers, the Athrotaxis, which really are fire-sensitive. They can't handle fire. So you've got the meeting point here between Eucalyptus, which is finely tuned in to taking advantage of fire, and Athrotaxis and other fire-sensitive rainforest species that really can't handle too much fire at all. And our research here has actually given us an indication that it can take up to 800 to 1,000 years for an Athrotaxis-dominated rainforest to recover after disturbance from fire, which is a really long time. That's one of the reasons that the data that we collect, the paleoecological data, is so important for understanding the ecology of these systems, because we just don't have observational data going back that far, empirical observational data. So those fires, those sort of ENSO-related fires, the El Nino-related fires, have slowly allowed these eucalypts to march in further to the wetter zones of Tasmania, where rainforest would normally occupy. So this here, the climate here, can more than accommodate rainforest, but it's this eucalypt forest all around us. This whole place is dominated by eucalypt forests. But in the ecological terms, that means that this area here, at least climatically, is bistable. It's able to host either a rainforest vegetation state or this eucalypt forest state. And in these sort of bistable areas where you can have two different vegetation states that are reinforced by very different feedback mechanisms. Here, eucalypts, flammable, they promote fire, keep out the fire-sensitive species, they're relatively fast-growing, they dominate and create this cycle where as long as there's an ignition source, and there's been people around these parts for at least 40,000 years, so there's always been an ignition source, plus the climatic lightning strike fires. So that creates a positive feedback and holds this system in the eucalypt state. Conversely, the rainforest systems, they're have low flammability in their fuels. They will burn if they dry out enough, and that's where those long, prolonged phases of sort of El Nino drying out enable rainforest to burn. But generally speaking, they have low flammability, they have a very closed canopy, which means they get a more moist understory, moist soils, and that's a fire retardant. And you get that positive feedback between more trees, more rainforest trees dominating, lower flammability, less fires. And you have these two essentially stable ecosystem states. About 3,000 years ago, this system was burnt. It had been burnt, every 1,000 years or so since at least 8,000 years ago. And then about 3,000 years ago, the system finally collapsed. The rainforest system finally collapsed, and these eucalypts spread out everywhere. The interesting thing is, there's a little site over here where next door, we have one site where this happened at about 3,000 years ago. Right next door, it didn't happen. It was burnt. It actually burnt a couple of times more than the site that did turn into eucalypt forest. And what we've found out through our data is that eucalypts were absent from that site. This is a really, really important finding. It tells us then that in the absence of a species like eucalypts that can engineer a change in the fire regime, that rainforests will just recover. It'll recover given a long enough time period. So the site where the eucalypts were absent, it burnt, and then about 1,000 years went by and it hadn't burnt again, and those fire-sensitive rainforest species moved back in. Whereas the other site, just over the other side of the ridge, had the eucalypts, and it transformed. After every fire, eucalypts increased a bit more. Suddenly a threshold was hit, and the ecosystem switched. Now, ecological terms, that's a bit of gold, that is, because we often don't have, especially in these vegetation systems, we don't have enough information through time from our observations. We haven't been doing ecology long enough to get a grasp of how these systems operate, what rhythm they beat to. So from our long-term data that we get out of lakes and things like that, we've actually discovered that you don't only have to have the fires, you need these ecosystem engineers, these ecological engineers, to be present in order to affect a switch. And that's some data that we've recently acquired. All right, I'll speak to you later.